In this video, we're going to model exponential decay. So a sample of bacteria is being eradicated by an experimental procedure. The population is following a pattern of exponential decay and approaching a population of 0. If the sample begins with 500 bacteria and after 11 minutes there are 200 bacteria, how many minutes will there be 50 bacteria remaining? So they give us a lot of information. First thing we need is our exponential growth model, our exponential decay model, which would be P of t equals P of 0 e to the kt. And we need to start writing down our information. Now they actually give us two scenarios here. The first scenario is what happened when 500 bacteria went to 200 bacteria in 11 minutes. So I'm going to write that as problem 1. And let's write down all the stuff that we know. We started with 500 bacteria, so that's P of 0 is 500. And P of t was 200 at the end. Our time was 11 minutes. And the thing we didn't know was K. And then they gave us a second problem. And in the second problem, we know that P of 0 was still 500. We don't know the ending amount. Well, actually, we do know the ending amount. They say 50, so that's P of t is 50. We don't know the time because that's what they're asking for. And we also don't know the growth or decay rate. So you can see that we can solve problem 1 to find the decay rate, and then once we find the decay rate for problem 1, we can then use that decay rate to find the time in problem 2. So we'll start with problem 1. We'll write down 200 equals 500 e to the kt, so that'd be 11k. We're going to divide by 500 to start. And that'll be 0.4 equals e to the 11k. And then we're going to take the natural log on each side. So natural log of 0.4 is going to equal the natural log of e to the 11k. This is the log law. We have log base e of e. That's just 1. Also, we can use the power rule to move 11k to the front. So this cancels and 11k comes to the front. So we just end up with natural log of 0.4 equals 11k. Then we can divide by 11 on each side. That's going to leave us with k equals. We need to plug that in the calculator. So we have a natural log of 0.4 divided by 11. It'll give us a long decimal. I'm going to write out a short version of this, a rounded version, just to use for the algebra purposes, but I'll use this number to figure out the rest of the problem. So let's write down the k value for each of these. That's negative 0.0833, negative 0.0833, and then let's solve problem 2. So we can say 50 equals 500 e to the negative 0.0833 t. We're going to divide by 500. Take 50 divided by 500. That gives you 0.1. So we have 0.1 equals e to the negative 0.0833t. We're going to take the natural log on each side. And this is a log law. Log base e of e is 1. Also, we can use the power rule to move the exponent to the front. So that'll be natural log of 0.1 equals negative 0.0833t. We're going to divide by negative 0.0833 on each side. And that's going to leave us with t equals. I'm going to plug that in the calculator. So I'm going to say natural log of 0.1. And I'm going to divide it by the answer I got earlier, the long decimal piece of this. And it gives you 27.64. It says round your answer to the nearest whole number, so that'd be 28. And that's 28, we're talking minutes, so it's 28 minutes it would take to drop that bacteria from 500 down to 50.